Okay, so our first question is asking us, Tom was chasing Jerry off a table that was 2.3 meters from the ground, and Jerry stops and Tom falls off at a speed of 7 meters per second. And the question asked is, where did he land? So we're looking for our change of x, which is right there. Actually, let me change that and use some cool neon colors, new neon colors. Quick, awesome. It's going to be barely seen. I'm not going to use that for the rest of the thing. Okay, so here we have 4 directions, which is our 2 planes of motion, which is our x-axis here, and I'll do that in blue, and I'm going to do this in orange. Our y-axis is going this way, up and down. So what we're looking for is the vertical movements, because we're asking how far did he land. We already know how high he is and how high he's going to drop, but we want to know how far he lands as far as the x-axis is concerned. So that's my dog snoring, please ignore that. So when we try to find out the distance, we're looking for average velocity equals distance over time. So that's the simple equation that we've known for the longest time since we started kinematics. So we know the average velocity is also known as VI plus VF divided by 2. So we remember that's how you can find the average of anything. So if I weighed 168 and my friend weighed 169, to find out the average between us, you would add them both together, divide by 2, and the average between us would be 168.5. Here, we look at the first law of motion, which means that an object in motion stays in motion until a force acts upon it. There's no forces that act upon it, so this also answers the second part of the question. The beginning velocity, horizontal velocity, is 7 meters per second, and the end velocity is 7 meters per second as well. So 7 plus 7 equals 14, divided by 2 equals 7 once again. So our average velocity is 7 meters per second equals distance over time. We neither have the distance, we're looking for it, we don't have the time. But because we're given the length of the drop, which is 2.3 meters, we can find out our change of y, which means our point from here, time through our change of y from point to here. Because even though the trajectory or the distance is different, like this distance here on the change of x is different than the change of y, the amount of time will still be the same. So we already know he's going to drop 2.3 meters because he's 2.3 meters high. But we just don't know the displacement here. But regardless of whether we're looking for the change of the horizontal axis or change of the vertical axis, the change of the time will always be the same. And here we have our vertical change of y. So here we have change of x is always our displacement this way, change of y is always our displacement this way. Change of y equals, here's one element, our initial velocity multiplied by time, and the second element is 1/2 acceleration t squared. So I'll give you some time or pause the video to write down this equation for vertical change of y. It's important that you know that equation. Okay, so what are we given? We're given already the change of y, because the change of y will always be 2.3 because he's 2.3 meters from the ground. So we're going to write in 2.3 equals our initial velocity multiplied by time. Do we have our initial velocity of it going downward? Well, we have it going horizontally, but that's for horizontal. We don't have it going downward. But wait, we do know this, that you remember when we were talking about free fall, and if I threw a ball up into the air, right before it changes directions and starts going towards the ground, the peak of free fall is 0 velocity. So here at the peak, it's 0 v going down the y. It's 0. So if it's 0 multiplied by time, obviously is 0, plus 1/2. And the acceleration of our y-axis is, what's gravity? 9.8. 1/2 9.8 t squared. And so here we have enough to find out our change, our time, our change of time. So let's go ahead and start the equation over here. Here we have 2.3 meters, and it equals 0 times time is 0, so that's 0, plus 1/2 9.8 t squared. So the first thing I want to do is I want to bust out my trusty calculator. And what we're going to do here is do 9.8 times 1 divided by 2. And what we get there is 4.9. So, oops, sorry. So what we're going to put here is 2.3 equals 4.9 because I multiplied 1/2 and 9.8 t squared. And the next step to isolate the t is to divide by 4.9, divide by 4.9. This cancels out, and we end up getting, here we go. Let's look at the calculator again. 2.3 divided by 4.9. And that gives us 0.693. So let's put 0.693. So we have 0.4693. Sorry for mispronouncing that, but you saw in the calculator, that's what I got, is equal to t squared. So if we just want t, we simply put a square root over that and square root both sides. So then we end up getting t equals, so let's go ahead and put that in our trusty calculator again. Second square root of 0.4693 equals 0.685 seconds. So we write that in there. That's the time of our whole equation, 0.685 seconds. Now check this out. Time on either axis, whether it's y or x, is always the same. So I'm going to grab this time here, and I can plug it into here. So what I end up getting for my equation on this side is 7 meters per second equals distance, or our change of x, which is what we're looking for, divided by 0.8 or 0.685 seconds. And when we do the math correctly, can you see that? Yes, you can. We multiply by 0.685. That crosses out. What you do to one side, you do to the other. 0.685. So you simply multiply 0.685 by 7 meters per second. Seven times 0.685. 4.795 meters. So this change of x equals 4.795. Do you see that? Now it looks all messy because it's all on one board, but as you can see, it makes logical sense. And if you don't understand it, go ahead and rewind it again. The second part of the equation says, what is Tom's speed before he hits the ground? Well, his speed here is 7 meters per second because there is no force acting upon it, so it just stays at 7 meters per second. So his speed when he hits the ground will be the same. Now let's move on to question 2. Okay, so for the next problem, we see that a car runs off the edge of a table that is 1.278 meters high, and it lands 0.372 meters from the base of the table. The question is asking for our change of time. How long does it take for it to fall? Now, it's very interesting to me. We don't have a velocity for our x-axis, so it's obviously, this is just to throw you off. We're not talking about we don't need our our x-axis, so we don't need any of those equations in order to find out the time. We can use the previous equation that we used on the other question of change of y equals initial velocity multiplied by time, and then our second increment is plus 1/2 acceleration times squared. And remember, know that equation one more time, because we're given our change of y-axis right here. Bless you, wife! Okay, so we have it's allergy season. We have our change of y, which is what? 1.278. So we have 1.278. And that equals our initial velocity multiplied by time. But remember, as we stated earlier, at free fall, at the peak of free fall, our velocity is 0. So we have 0 multiplied by time plus what? 1/2. What is our velocity? 9.8. Or what is our acceleration? Yes, that's right. 1/2 9.8 t squared. So I put that all in 3 different colors. My green marker is futilely failing from me, so I'm going to use purple instead. 1/2, and that's so much better, 0.8 t squared. Okay, I'm going to plug in everything in the calculator. Here we can see that 0 multiplied by anything is 0, so we're going to sit there and take out that, and we have another equation here of 1/2 9.8 multiplied by t squared equals 1.278. Let's go ahead and bring out the trusty calculator again. Of 1/2, 1 divided by 2, multiplied by 9.8, and what we get is 4.9. So here we're still going to use purple. We have 4.9 t squared. And remember, to isolate the t, we're going to divide by 4.9, divide by 4.9. These cross out, and so we're isolated with just t squared. And we put in the trusty calculator, 1.278 divided by 4.9, and we get 0.268. So let's go ahead and write that new number in. 0.268 equals t squared. Now, to isolate t one more time, to just get t, we put that underneath the square root. And then if we do that in our calculator, second square root, 0.268, we get, no, that's the wrong one. Hold on. Second square root, apologies, 0.2608. There we go. We got 0.51 seconds. Yeah, because that's supposed to be a 0.8. Sorry. 0.8. And so what we end up getting is our change of time ends up equaling, as we saw in our calculator, 0.5106. So I'm going to go 0.51 seconds. And that is my change of time. Now, we have the change of time here. The second part of the question is asking, what is my horizontal velocity? And remember what we said earlier, that our average velocity equals d over t. That equation will never ever fail us. But here we have our distance, and here we have our time. So we simply make this equation, our v here is going to be, what's our distance? 0.5372. This is what's going to equal. And we divide by our time, which is 0.51. So let's go ahead and do the math. Here we go. 0.5372. Oh wait, why does it say 1.5? 0.5372. That's our velocity, or that's our displacement of x. That's our change of x right here, what we're given in the beginning. We're going to divide that by our time, which is 0.51 seconds. And that's our velocity right there, 1.05. So our velocity here equals 1.05. And that's what you get for those two answers right off the bat. Moving on. So here in the next equation, we're talking about collinear vectors. And here we see that a person in the passenger train is traveling at 13 meters per second in a direction this way. Doesn't matter what direction. And it also says it's not relative to the Earth, meaning that we're not taking in gravity and all the other factors like air resistance and all that other stuff into the equation. We're simply saying that we're acting with the Earth itself, if in a perfect world, if everything was acting with itself. 13 meters per second in an opposite direction. He throws a ball at 18 meters per second. And it says, what is the velocity of the ball relative to the Earth as it leaves the thrower's hand? So since it's moving in the opposite direction, you simply take the net. You take 18 minus 13 meters per second, and what you end up getting is 5 meters per second, and that's the speed of the ball in this direction, in the opposite direction of the train. So that equation is quite simple at 5 meters per second. Okay, in this question we're talking about a ferry that's moving up north at a velocity of 2.3, and it's going against a current eastward at 3.2 meters per second. And what that does is it creates a right triangle, and we're trying to find out the magnitude between the boat and its destination relative to the Earth's surface. So we basically just do the Pythagorean theorem, and we do 2.3 squared plus 3.2 squared, and we square root all of that together. So if we want to do the math together, we can do that math together. 2.3 times 2.3, and that equals 5.29. So let's go ahead and write that down. 5.29 plus, we're going to do this one now. Clear. 3.2 times 3.2, and that equals 10.24. 10.24. And what you end up getting there is plus 5.29. 15.53. We square root that. Second square root of 15.53. What we end up getting is 3.94 meters per second. And that's our magnitude here. The first part of our question will be 3.94 meters per second, and that's our magnitude there. Now the next part of the question is asking, what is our angle? What is our angle? At what angle does it move, or what in which direction? So what they're asking for is which angle is it going when it's moving northeast. So it is moving northeast, but we want to find out the angle. Oh, it's just telling me that it's very low on battery. So we want to find out the angle. So what we're going to do is we're going to we have our hypotenuse, and we have our opposite, we have our adjacent, and we have our hypotenuse. And we could use either one to find out the angle. But for now, we're going to use this equation. Tan -1, and it's going to be multiplied by our opposite over our adjacent. So first, let's do the math there. Clear it out. What's our opposite leg? 3.2. What's our adjacent leg? Divided by 2.3. We get 1.39. So here we get 1.39. Okay. So we just simply negative tan, because we're looking for the angle. Negative tan, 1.39. And what you get is 54.26. So we're going to use 0.27 to round up. So the angle here your answer for the next part is 54.27. We're going to round that up. Degrees. That answer needs to be put into degrees. So that's how you find the angle in magnitude, and this is how you combine the two vectors together and calculate your magnitude of the object in motion. Okay, so this is the last part of our worksheet, and what it's talking about is a long jumper jumps at an angle of 19.8 degrees with a velocity of 9.67 meters per second. And what we need to find out is the distance that he jumps. So we're looking at our what axis? Our x-axis. So I already put it in here, but here's how we're going to figure this out. If you're given an angle, and we know that this is a right triangle, if you're given an angle, this is like back to trigonometry, and you're also given the length, or in this case the velocity at a certain point, you can find out the lengths of the other two legs simply by using sine and cosine. So if you sine the angle, sine angle of 19.8, that'll equal the opposite leg. So this is our angle here, our opposite leg, over our hypotenuse. And we're given our hypotenuse, we're given our angle, and we can figure out that by balancing out that equation after we put sine 19.8. So just put sine 19.8 in your calculator, and then you get a certain number, and then with that you balance it out, and you'll get 3.275 for your opposite leg and your adjacent leg, which is your x velocity, for 9.1. So looking back over here, since we're looking for our change of x, our change of position, our our position initial and our position final. If we look over here on this side, which is where we're going to have our final step, I rearrange the equation. Velocity equals displacement over time. And if we rearrange it, we'll get displacement equals velocity times time. So this right here, I don't want you to just get it twisted, that this is triangle V equals triangle X over T. And then eventually we just rearrange it, and this is what we get. X equals V times multiplied by times. Now, we have our velocity because we just figured it out by doing our sine and cosine of this right triangle. But we don't have our time, and we're going to have to go back to the y-axis equation. In this middle part right here is the y-axis part of our equation to figure out the time. Because remember, as we discussed in an earlier problem, time is the only thing that can jump from one axis to the other, because it's happened simultaneously. Okay, so here we have the equation, change of velocity equals over time equals acceleration. Okay, well, on our y-axis, change of velocity is v minus I, vf minus I, so your final velocity minus your initial velocity divided by time equals acceleration. Or, now let's get rid of the t on the bottom. Those two cancel out when you multiply that by t. I hate to show you the vanish, so I'm going to do that one more time. When we do to one side, we do to the other. But these cancel out. So what you end up getting is v. Oh, that's kind of off. So I'm going to, yeah. Okay, so what you end up getting is vf minus vi equals acceleration, your acceleration multiplied by your time. So here we have in the equation vf minus vi equals acceleration multiplied by time, but we just want the time, right? So let's go ahead and rearrange it one more time. We can divide by triangle A, and we'll divide that by triangle A, and these two cancel out. So we end up getting time equals our final velocity minus our initial velocity divided by triangle A. Now, here's the tricky part. No, it's not really tricky. Remember how we talked about at the very peak of the trajectory of y, the velocity is 0. So our final velocity going from here to here, remember our direction is what? Our direction is upward. our final direction from here to here is 0. So repeating over here. And we subtract it by our initial velocity, in which we figured out by using sine and cosine, once again for the opposite leg, which is 3.275. So we have 3.275 meters per second. Okay? And that's all going to be, let's extend the box here. That's all going to be divided by what? And this is what's going to equal our t. That's going to be all divided by our acceleration. And we're like, okay, well, our acceleration is 9.8. But remember, gravity is an acceleration going downward. And because we're going upward, it's going to be a negative 9.8 meters per second squared. I'll repeat that one more time. Earlier, we did a problem to where we started up here and then we calculated the downward, and our 9.8 was positive. That was because we were gauging our velocity going downward. But since we have a velocity going upward, gravity is in the opposite of us, so we go negative 0.9 or 9.8. So let's go ahead and plug this into our calculator. We have 0 minus 3.25 obviously is negative 3.275. So let's put that in the calculator. Negative 3.275. And then what we're going to do is divide by negative 9.8. And what that equals out to is 0.334 seconds. And that becomes an important value again. So our time total is 0.334 seconds. And remember, what we do, that time is simultaneous to this time, so we can plug that in there at 0.334 seconds. So we multiply this time by our velocity on x. Here we go. 9.1. 9.1 is our velocity of x, multiplied by 0.334, and we get 3.039 meters. So our displacement right here, this and this, change of x, equals 3.04 meters. And that's the first part of our equation. Next, it asks for our maximum point going upward. Remember that we're going up at 3.275 meters per second. But what we're going to do is we're going to use our old equation that we discussed earlier. Do you remember this equation? That our triangle y of axis equals our velocity initial multiplied by time plus our 1/2 change of acceleration t squared. And one more time, I'm going to give you some time to write that down. We just look at this. We got our change of y. This is what we're looking for. We're going to take our VI initial, so we're going to take that, multiply it by our time, and then we're going to add that to 1/2 plus acceleration, right here, t squared. So when we write out the equation, it actually looks like this. We have 3.25, 275. I keep saying that, but just pay attention here. And I'm saying, gladly I'm writing it right. So our triangle y, our maximum point from this point to this point, is that, and what did we say our time was? Or we said our time was 0.334, right? And then so we're going to add that to 1/2, and our acceleration is negative 9.8 because we're trying to go up and we don't have wow, that was my dog. And the acceleration is gravity going down, And then here we have 0.334 squared. So, as you can see, I just simply plugged in the numbers. If we plug in everything, you can type it into your calculator with me, just to make sure that we're getting the right answer. We have 3.275 times 0.334. That equals 1.093. 1.093. And we're going to add that to this. Here, we're going to show you that we have a negative 9.8 multiplied by 1 divided by 2, basically 1/2. You get a negative 4.9. Negative 4.9. And you're going to multiply that by 0.334 squared. So let's do that squared part for it. 0.334 times 0.334. And that equals 0.1115. So we're gonna just condense that to 0.112. And then now we multiply those two together. 0.112 multiplied by negative 4.9, and that equals negative 0.55. So now we're condensing. Negative 0.55. So if you add a negative, it's the same thing as subtracting. So let's subtract that. .093 minus 0.55, and we get a total of 0.543 meters. So your change of y right here, which is the answer to your last question, make sure I put it in something you can see, is 0.543 meters. And that is your change of y. That's the highest it goes this way. Alright, congratulations. We have just learned trajectory motion.